Today's, today's lesson is on stars and bars. And first, I'll go over some basic counting. So there's a there are first a few definitions we should know before we move on, especially because stars and bars is related to these basic counting definitions. So combinations are the number of ways to choose p objects out of n objects where order does not matter. This is very important. So that's what makes combinations different from permutations. The formula for combinations is n factorial divided by p factorial divided by n minus p factorial. And if you didn't know what p factorial was, I guess n factorial equals n times n minus 1, n minus 2, ... times 1. So it's the product of every single integer below, or positive integer below n and including n. So that's what this funny looking, I guess, exclamation mark means. And so it can also be written as n choose p. That's what it's. So people will say n choose p, and then this is what they mean. So, okay, moving on. Permutations. A permutation is, a permutation. The number of ways to choose p objects out of n objects and arrange them in a line. This is where order matters. So order matters is a really important thing. And a permutation, let's say you have four different balls. Let's say a red ball, a green ball, a white ball, and a black ball. And if you want to find the number of ways to permutate them or arrange them in a line, this would be 4 factorial, because if you think about it, we have 4 spots, and the first spot has 4 options to choose out of these 3, but then the next one only has 3 options because you already used 1, and then 2, and then 1. So 4 times 3 times 2 times 1, or in other words, 4 factorial. But if let's say you have red, blue, and white, this would be different because you have to, because you have this n minus p factorial, and essentially we have to divide by 2 factorial because there's a repeat of 2. So this would be using the same logic as before, but divided by 2 factorial. So that's one application of permutations. Here's a problem. How many ways to choose 1 president, 3 vice presidents, and 1 secretary from 10 AYMC members? So here's the solution. Note that we don't really care about the order of the vice presidents, because since we're just choosing. Say I have like 3 things, A, B, C, or let's say 4 things. And if I choose 2 things, that means A, B is equivalent to choosing B, A. So like order doesn't really matter. So that means, since order doesn't matter, that means we're doing combinations. So after we choose a president and 3 vice presidents, there's 6 people to choose from. So what we're doing is we're first choosing the president. It doesn't really matter what order we do them in, but let's just start with the president. So we have 10 people, and we need to choose 1 for our president. And now we have 3 vice presidents to choose. But since we already chose 1 from the 10, we have 9 left, and we have to choose 3 to be vice presidents. And now we have to have 1 secretary, so we have 6. So we have 6 different people to choose 1 from. So this will be our answer, and this is 5,040, which also happens to be 7 factorial if you memorize your factorials. I'll list out the first few factorials. Actually, 1 and then 2. So this is 1 factorial, 2 factorial, 4 factorial, 5 factorial, 6 factorial, 7 factorial, 8 factorial. So 3 factorial is 6, 4 factorial is 24. You don't need to memorize these, but it's just like good to know in general. 5 factorial is 120, 6 factorial is 720, 7 factorial is 5,040, 8 factorial is 40320, 9 factorial, well, you could just keep going on and on. You just multiply by the next number. So here's another problem. There are 3 sports teams: basketball, soccer, and football. How many ways can 12 people join the teams if people are distinguishable? That means we can tell people apart. So like person A, that means that person A is not equal to person B. Well, that's kind of obvious, but this is pretty important because let's say that we're dealing with like identical tennis balls or something. That means if you assign variables to tennis ball, like say tennis ball A, it does equal tennis ball B because tennis balls are all the same. Unless you're playing with really bad tennis balls, which I hope you're not. So if we have 3 sports teams, let's go through the solution. Each person, so let's say our 12 people are person A, B, C, D, E, F, G, H, I, J, K, L. That's 12, right? Yeah. Let's say these are our 12 people, each of these variables. And so each person, so A, can either join the basketball team, the soccer team, or the football team. And person A has 3 choices. And now person B also has 3 choices, and C, and D, and it keeps going on until L. And since we have 12 people, we have 3 to the 12, which is our answer. Well, now we have stars and bars, which I guess Tina will go over. But if you have any questions about like these formulas, just like let me know or something. I'll type them into the chat so you guys have them to reference. So yeah, I guess it's Tina's turn now.
Okay. So can everyone see this? Okay. So let's change up the original sports problem a little bit. There are 3 sports teams that are still basketball, soccer, and football. How many ways can 12 people join the teams if people are indistinguishable? This means we cannot tell people apart. Like if Alan and Darwin are on the basketball team, this is the same as Alan and Daniel being on the basketball team because there's 2 people on the basketball team in both scenarios, and we only care about the number of people on each team, not who joined the teams. And this is very similar to the problem above. I'll give you some time to think about it, and if you have ideas, you can send it to me in the chat. While you're still working, I'd like to say that usually when a problem talks about people, usually the people are distinct. Like in the previous problem, where Alan and Darwin being on the basketball team is different from Alan and Daniel being on the basketball team. And usually things that are the same, like pennies or candy, will be indistinguishable unless they have colors or type of coins or stuff telling them apart. But in this problem, the people are indistinguishable. This is great. Some of you already know this and already received a few answers. So I'll go ahead and explain. So like, we know that the teams are different, but not the people. So if we draw a diagram about how to sort this, there's the 3 teams, basketball, soccer, football. There's 12 people that I represent with identical red balls because we only care about how many red balls goes into each team. So to make it easier and a little more like something we already know how to do, how about I represent these teams as dividers that divide the people up into teams? But if I have 3 teams, I need 2 dividers because let's see. I need 1 divider to divide between the basketball and the soccer people, and 1 divider to divide between the soccer and football people. It doesn't really matter what order you put the teams in. You just give them a set order. Like in this one, it's basketball, soccer, football. It really doesn't matter. So all the balls that get put behind this first divider join the basketball team. Like right now, there's 3 in the basketball team. The balls between the 2 dividers get put in the soccer team. And the rest of the balls, which should be behind the second divider, get put in the football team. Is it clear why we have 2 dividers for 3 teams? In math, this is also called a bijection when we turn a counting problem into a different problem. It's the same problem, but phrased in a different way. Like we turned the teams and the people into balls and dividers. So now what we can do is we can order the balls in the dividers. I have a better diagram like this. This represents that 3 people join the basketball team, 3 people join the soccer team, and 6 people join the football team. And it is also possible for everybody to be on one team or one team with no people. That is, if we have something like this, where there's a divider, no balls behind this divider, some balls, this, and some balls. This just represents there's nobody on the basketball team. Does it make sense so far? So all we have left to do is to find the number of ways to order 12 balls and 2 dividers, which is 14 choose 2, because this is like the definition of a combination. So the answer would be 91. Great job to everyone who got it. And in general, the number of ways to assign P indistinguishable items to indistinguishable items is n plus P minus 1 divided by n minus 1 factorial times P factorial. The n plus P minus 1 comes from there's n indistinguishable objects, P distinguishable objects, minus 1 because there's P minus 1 dividers for P objects. And in the end, there's going to be n minus 1 dividers, so we divide by n minus 1 factorial, and P distinguishable more typos, P minus 1 dividers and n indistinguishable objects. And it's n plus P minus 1 because there's n minus 1, P minus 1 dividers to divide into P groups. And now let's move on to some examples.
Okay, so our first example problem is how many ways are there to give 6 jelly beans to 5 kids? So I guess I'll give like a minute for this problem and then I'll explain it. Only a minute because I guess this is an example problem. Also note that it is possible for a kid to have 0 jelly beans. That is very important. Okay, it looks like I've gotten some answers. So we have 6 jelly beans, and like we did above with this example, we can make a bijection and change our jelly beans into, let's do purple balls. So we have 6 purple balls. And since we have 5 kids, we need to separate, well, these purple things represent our jelly beans now. And wait, let me I need to share again. Okay. Okay, so we have 6 jelly beans. We denote them as 6 different jelly beans. And we can see that we have wait, this is a typo. This should be 4 dividers, I think. We have 4 dividers. We have 4 dividers for 5 kids because you only need 4. Let's say 1, 2, and then 3, 4. And now we have 1 section, 2 sections, 3 sections, 4 sections, 5 sections. So you only need, if you have like 5 different or n different categories, in this case, our category is for kids, n. The number of dividers is n minus 1. So that's kind of important to note. So let's go back to the 6 jelly beans. And we have, we need 4 dividers. 1, 2, 3, 4. This means that the first kid gets 1, the second kid gets 1, the second kid gets 1, and the third kid gets 1, fourth kid gets 1, and the lucky 5th kid gets 2. So if you think about it like this, let me undo this. Oh, not that. Since we have six jelly beans and we have 4 dividers, the total amount of objects is 10. So we have 10 different spaces. 10 spaces, and we need to choose 4 of those spaces to be our dividers. And like a divider could be here, jelly bean, divider, jelly bean, divider, and maybe a divider, jelly bean, jelly bean, jelly bean. So we're basically choosing where we want to put our dividers. We have 10 total objects, so we have 10, and out of the 10 spaces, we choose 4 of them to be our dividers. So the correct answer is 10 choose 4. So, and 10 choose 4 is, let me recompile. Yeah. Our answer is 10 choose 4, which is 210. You can do that by 10 factorial divided by 6 factorial, 4 factorial. And then from here, you know that 1 times 2 times 3, 6 times 7, 10. I'm just leaving in a few like dots. You know what's going on there. And then 1 times 2 times 3, times 6. And then 1 times 2 times 3 times 4. And notice that the tops, they both have 1 times 2 times 3 times 4 times 5 times 6. So does the bottom. So this becomes 7 times 8 times 9 times 10 divided by 1 times 2 times 3 times 4. Notice that 2 and 4 make 8. 3 goes away because of 9. And anything divided by 1 is itself, so that also goes away. So we have 7 times 3 times 10 is our answer. And that is precisely 210. Okay.
This problem is a stars and bars problem because the kids are dividing up the jelly beans again, but there's some restrictions. First, we give 1 jelly bean to each kid, which would result in 3 jelly beans left, like shown on the screen. And then there's 2 dividers because 3 kids equals 2 dividers. And this time, if it looks like 1 kid doesn't have a jelly bean, in reality, they already have 1 jelly bean because we gave each kid 1 jelly bean at the start. So the answer is 5 choose 2, which is 10.
Yeah. So this like theme of like giving, like if they are required to have some amount of some object, like if this was generalized to, yeah, okay. If this was generalized to, let's say, I think there was an AMCA problem, like you have 20, or yeah, 20, let's say jelly beans, and you have 3 people. Let's denote them as A, B, and C. And I think the problem was like asking if each person, or how many ways can you give the jelly beans to A, B, and C so that each one has at least 2 jelly beans. And the trick is that you give 2 jelly beans in advance. So since we gave 6 away, now we have 14. and now we basically have just 14 jelly beans to 3 people, including 0. And well, if you know the formula, then it should be 14 plus 3 minus 1. Choose 3 minus 1, because this is the total amount of objects, and this is how many dividers you have. So yeah, on to the next problem. How many ways can you distribute 3 red lollipops and 2 yellow lollipops to 6 kids? I'll give you some time to think about this. And send me your answers.
Okay. So, like my hints said, this problem is a lot like the earlier problem where we had to take care of the restriction first. In this case, the restriction is about the order of the lollipops because 3 of them are red and 2 of them are yellow. And one kid having a red one and the yellow one is different from another kid having 2 yellow lollipops. So we ordered the lollipops first, and that would be 5 choose 2 because there's 2 yellow and 3 red. And next we give the 5 lollipops to 6 kids, which would be 10 choose 5 because it's 6 plus 5 minus 1 choose 6 plus 5 minus 1 choose 5. So the answer would be 5 choose 2 times 10 choose 5 because we can't forget about ordering the lollipops. We have to multiply the ways to order the lollipops by the ways to give the lollipops to the kids. And that would be 2,520. So it's ordering the lollipops first and then multiplying it by the regular stars and bars.
So here's our next problem. How many integer solutions are there to the equation x plus y plus z, where x, y, and z are all positive? Okay, I'll explain this one now because this is a relatively easier problem in the world of stars and bars, I guess. So we have x plus y plus z equals 8. And we can separate 8 into 8 ones. So we have a 1, 2, 3, 4, 5, 6, 7, 8. And we have 3 categories, or 3, I guess you can consider these being our jelly beans and X, Y, and Z being our football teams or something. I don't know. Basically, we have 3 objects or 3 categories, and so we need 2 dividers because if you have n objects, you have n minus 1 dividers. So we have divider and maybe another divider. So this means 1, 3, 3, and 4. Those are our 3. This would be an example case. And we have 10 objects total because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So we have 10 objects, and we need to choose 2 spaces to be our dividers. So 10 choose 2 is our answer. And that is, wait. Oh yeah, I did it wrong. So this includes 0. Let me go back. I forgot to mention that. So, right. So we ended up with 10 choose 2. But in reality, this should be 7 choose 2 because like the problem above here, this problem, let me clear. Like this problem, we need to give the people 1 jelly bean. In this case, we need to give the people 1, I guess 1, considering we have 8 ones. So since we already gave 3, because there's 3 ones away, because there's 3 categories, now we have 7 and 2 dividers. So it's 7 choose 2. That is 21. So Yeah, even I make mistakes a lot, actually. Oh, yeah, and our next problem will be
So our next problem is how many integer solutions are there to the equation x plus y plus z equals 8, where x, y, and z can be non-negative, which means they can be 0. It's very important in math competitions to know that positive integers or counting numbers refer to anything greater than 0, which does not include 0, but non-negative includes 0.
okay. So how do we do this problem? The hint I gave was that this is my mistake, and basically let's do the same thing. Let's separate our 8 into 8 different ones, and since they can be 0, we don't need to give any of the or any of the categories X, Y, Z. We don't need to give any of the categories um, any of these ones beforehand, like we did up here. And so since we have three people, uh, and 8 ones, 3 plus 8 minus 1, choose 3 minus 1, or 10 choose 2 equals 45. So yeah, that's how you do that one. And yeah, I'll go to the next problem. What if x, y, and z are all greater than -3? How does this affect the problem?
Okay, this problem, it seems kind of intimidating with the -3, but like the earlier problems, we just have to figure out how to deal with it. We know how to do stars and bars with non-negative numbers because we don't know how to put -3 things behind the divider. So first, we add 3 to each x, y, and z. This is like giving each kid 3 candies because they all want at least 3 candies. Like x, y, and z all want at least 3 extra numbers so they can be non-negative. But after we add 3 to x, y, and z, we have to add 3 to the other side of the equation. So it turns into x plus y plus z equals 17 because it was originally 8, but now I have to add 9, so it's 17. Now we can use stars and bars. There's 17 stars and 2 bars, which gives us 19 choose 2, which is 171. Let's move on to the next problem.
Okay, our next problem is how many terms are in the polynomial x plus y plus z to the power 9? Okay, so this problem, I'll scroll down first so you guys can see how some people do it. So we have this, well, we can't really just expand this because that'll take forever because you have the power of 9. But when you expand a polynomial raised to a certain power, you know that because all these have power 1, so this is in other words, x to the 1 plus y to the 1 plus z to the 1 to the 9. We know that because this is just 9 of these multiplied together, because the maximum power of each one, they're all 1, and we have 9 different like things being multiplied, we have a total power of 9 in each of our expansion. So like it doesn't really make sense if you just do that. So the examples here, like the very first term of this expanded out is x to the 9. And then it'll be plus some coefficient, let's say C1, times x to the 8 times y. And this is also y to the 1 plus C2 x to the 8 z to the 1. And notice that the sum of each of the powers is always 9. So x to the 9, x, y to the 5, z to the 3. There's also 1 on the x, so that's still 9. And x to the 7, z squared. So this means that we have a stars and bars problem where we have 9, 9 powers, you could say. Let me clear. If we have like 9 powers, let's separate it into 9 ones. 3, 5, 6, 7, 8, 9. And since we have 3 variables, we have 2 different, we have, I guess, 2 dividers. So like this could be a divider, this could be a divider. So this be 3, 3, 3. This would correspond to x cubed, y cubed, z cubed. And so we have 11 objects. So it's 9 plus 3 minus 1. Choose 3 minus 1 equals 55. But yeah, but here it says 11, choose 9. So you might be thinking, well, like what's the difference? So like, let me clear. If you have 11, choose 9 is equal to 11, choose 2, because 11, choose 9 is just 11 factorial, 9 factorial, and 2 factorial. And then 11, choose 2 is 11 factorial, but 2 factorial and 9 factorial. And these are obviously the same because multiplication is reflexive. So yeah, that's that problem. And our next one, we have practice competition problems now.
So first, know that a degree 6 polynomial looks something like a times x to the 6 plus b times x to the 5th plus c times x to the 4th plus d times x to the 3rd plus e times x to the x squared plus fx plus g, where g is the constant. And let's see that I haven't missed anything. Yep, they're all there. So if we plug f of 1, we would just get a plus b plus c plus d plus e plus f plus g, which in this case equals 30. And f of -1, we know that a is positive, but b would be negative because -1 to the 5th power is -1. So it alternates. So it's a minus b plus c minus d plus e minus f plus g. This equals 12. So we might be tempted to go ahead and do stars and bars on a plus b plus c plus d plus e plus f plus g equals 30, but we have to make sure that the f of -1 equals 12. So we know that if we add the equations or subtract the equations, we can get rid of some of the negative signs. So let's add them first. 42 equals 2a plus 2c plus 2e plus 2g. So a plus c plus e plus g equals 21. If we subtract the equations, we like 30 minus 12, we get 2b plus 2d plus 2f equals 18, which would mean that B plus D plus F equals 9. But the coefficients have to be positive integers, which means that when we do stars and bars, they can't be 0. They have to be at least 1, so we give 1 to each of them first. So in the A plus C plus E plus G equals 21 case, there's 17 stars left and 4 bars and 3 bars for 4 letters. For the B plus D plus F equals 9 case, we have 6 stars and 2 bars for 3 letters. This is 6 choose 2, which is 15. And this is 20 choose 3. Six choose 2 is not 8. 6 choose 2 is not 8. Okay. 20 choose 3 would be 20 times 19 times 18 divided by 6, which is 20 times 19 times 3, which is 570. So ultimately, the answer is 570 times 15, which my mental math is not that good. Okay, that looks right. Got it? So now let's move on to the fourth problem, where x plus y plus z to the 100th is expanded. How many distinct terms are there? And for this one, it's okay if you leave your answer as a combination, like something choose something.
So let me get out my drawing tool. You have a convex pentagon A, B, C, D, E. And we have 6 colors. And the ends of each diagonal must have different colors. How many different colorings are possible? So let's first of all, draw all of our diagonals. It's not that many. So we have 6 colors. I think the most optimal way would be doing casework. However, well, yeah, even though this is a start and bars class, you still might have to do casework because this class also covered, this lesson also covered like these basic counting things. So like permutations and combinations. And that's what this problem really goes down to. So you have to do casework on the colors. So let's call a color, let's call them 1, 2, 3, 4, 5, and 6. So A can be color 1, and that means D and C can be, or D and C can't be 1. So we have to, let's say D is 2 and then C is 3. Let me draw back these diagonals. And notice that this point can be 2, can't be 3. It can be 2 or 1. So let's just do casework and let's call this 1. And let's have another case where this is 1, 2, 3, and this is 2. And so in the case that this is 1, this one can either be 1 or it could be 3. So you have that, or one, 2, 3, 1, 2, no, 3. Yeah. And notice that these two are symmetrical. Well, not really, but this one, because this point has to be, this point can be 3, 1, or 4. Oh, that's nice, 3.14. This one can be 3, 1, and also 4. Yeah, so 4 being the other color. So notice that these two are like the same, except we switched 2 and 3. But since each point has like it's A, B, or C, or D, or E, they're different. So we need to just do one case and multiply by 2. And for if this is a 3, then what we really have to do is just 6 choose 3, because you only use 3 colors for this one as well. So times 2, and then 4 be plus 2 plus 6 choose 4. So this is the number of ways, and then this times 2, because this case and this case are like pretty much the same, but just reversed. And you have that 6 choose 3, if you don't know, that is 20. 20 plus 6 choose 2. This should be 6 choose 2. Wait. Yeah, 6 choose 3. 20 plus 6 choose 4, which is 15. So this makes 55. That's one case. I could like keep going, and like casework would take a long time to explain. So I'll actually just pull up the official solution. So we can do casework. This is like what I was going to do, because for A you can choose any of the 6, and then B they can be the same as A, or they can't, or they won't be. And it's like you use logic to separate it into cases. And I think this solution 3 looks like a pretty decent one. So case 1 would, in this case, would be there are no colored pairs. So like you have 6 different colors in 5 different spots. So that means if every color on each of the vertices is different. And then for case 2 is if there's one like pair, because like you should notice that in this problem, 2 vertices can have the same color. So that's this case 2. And case 3 would be if there's 2 color pairs, and then you just add them up and you get 3,120. If I explained all this, it would have taken a while. So If you didn't get that, I'll send that to you guys. Or actually, I'll do that. You guys can look that up on your own because I think the other breakout can probably see the messages. So I guess we could, if you guys want to, you guys can try this. How many degree 6 polynomials with integer coefficients are there such that f1 equals 30 and f negative 1 equals 12? So okay. I'll copy this and bring it down.
It's 6:30 already, so I guess we can go ahead and go. I hope you enjoyed this and thanks for coming.